Hello and welcome to today's session. So in the last tutorial, we have discussed on the amplifiers, that is inverting and non-inverting amplifiers. So in this tutorial, we are going to discuss on the another application of Opamps, that is summer. So let us switch back to our screen. So summer is nothing but an Opamp circuit where the inputs from the various sources we are going to add it using with the help of Opamp. So there are two types of summer circuits, or we can also call it as adder circuit. So there might be a summer circuit of inverting configuration and there is a summer circuit with non-inverting configuration. So now we will see this. The first one, we will see the first circuit, that is summer in inverting configuration. So let me write the circuit for this summer with inverting configuration. So we will be taking here the three inputs in our example, so which are connected through three resistors. And these are connected together, and these are connected to an Opamp inverting terminal. That is why it is called as a summer with inverting configuration. Now this output is connected back to an inverting terminal through a feedback resistor RF. Now the other terminal is grounded, that is non-inverting terminal is grounded here. So this is our V1 and the second terminal is V2. So there is a feedback resistance. So let us give names for these resistors. So let me call this as RA, this is RB, and the third resistance is RC, and likewise we will give the name, this is VA. We'll call the second source as VB and the third source as VC. So now we have the three sources and we have to add these voltages across these three sources, and we have to obtain the output across the V0. So let us see the mathematical derivation of this adder. So at this point, let us write, we will apply the Kirchoff's current law. So we know that the current entering at one node is equal to the current exiting from that particular node. So now here there are three incoming currents, that is I1, I2, I3 from these three voltage source, and the exit current is IF only. But just for notation we will write there is a one more current, we call this as IB, but we know that IB is equal to 0. Why? Because due to virtual ground concept, the V2 is connected to ground, so it means the internal resistance of this Opamp is very high ideally, so there is no current flowing through terminal V1, so the IB current is equal to 0. Anyway, let us apply the Kirchoff's current law and write this is equal to I1 plus I2 plus I3 is equal to, this is IB plus IF. So due to virtual ground concept reality, we know that V2 is equal to 0, due to which V1 is approximately equal to V2, therefore this is equal to 0, therefore we have IB is also equal to 0. Okay, so I'll move this circuit to the corner so that we can further do our analysis at any point of time. So now let us continue with our analysis. Before moving this, let me show you one thing. Now we will going to apply the node voltage analysis for each of these resistors. Now we see what is the voltage potential across the terminals of these resistors, that is the voltage potential difference across RA is, that is VA and V1. So we can write this as VA minus V1 by RA. Likewise for this resistor we will write, means we will be replacing this current equation with the node voltage analysis. So then we will get the equations. So now let me move this circuit. So then we will get, for this current I1 can be replaced as, that is VA minus V1 by RA, plus the current I2 can be represented as VB minus VB minus V1 by RB, and the third current I3 can be represented as VC minus V1 by RC. Now I will erase this all terms because we know this, and which is equal to the right hand side is IB is equal to 0, so only we left out with IF, so IF can be written as, that is V1 minus V0 by RF. Now with the virtual ground concept, we know that V1 is equal to 0, therefore we have the terms only VA by RA plus VB by RB plus VC by RC equals, here also V1 is equal to 0, therefore minus V0 by RF. So if you rearrange this equation, then what happens here is that, so I'll just move this equation to the right side, and when we rearrange this equation, then we have V0 equals minus of RF into RF, we can write like this, RF by RA into VA plus RF by RB by RB into VB plus RF by RC into VC. So this is our final equation for the summer of inverting configuration. Now if we consider a special case where if all these resistance value are same, that is RA, RB and RC value are same, that means that is RA is equal to RB is equal to RC. If all these resistors are equal to, say, some resistance R, then this equation finally reduces to V0 is equal to minus. So then I can take this as a common, then I can write this as V0 is equal to minus RF by R of the sum of the three voltages, that is VA plus VB plus VC. This is only applicable, the second equation is applicable only when all the three resistors are equal. Either we can apply this equation or this equation. The second equation is applicable only if this condition is, that is if all the resistor values are equal. Okay, so hope you have understood this analysis of summer of inverting configuration. So let me save this page, that is page 32. So now let us take a new page and let us see one example. So here one circuit is given. So we have one circuit here with the three input voltages. So these are connected to an inverting case or inverting terminal. Now there is a feedback resistor connected from output to input. Now let us define the values for these resistors. So the first one is 1 kilo ohm, the second one is 3 kilo ohm, and the third one is 2 kilo ohms. So the voltage here is, for the first one is 1 volt, second one is 2 volt, and the third one is 4 volts. And the feedback resistor value is 3 kilo ohms, and the V2 terminal is grounded. This is by default, this is a circuit for a summer of inverting configuration. So this is the given circuit. Now we cannot apply the second equation here. Why? Because the RA, RB and RC are not same, therefore we have to go with the first equation which we have derived. Therefore the V0 is equal to, therefore minus of, that is, we know the equation, that is RF by RA into VA plus RF by RB into VB plus RF by RB, RF by RC into VC. Now all the values are given here. It's a very simple calculation, so I request you to submit and you calculate. I don't have the calculator, so these values might be correct, which I have very long back calculated these values. So hope we should able to get this minus 11 volts across the output. Again, the minus symbol indicates that because all these inputs are connected across the inverting terminal through this V1 point here, that is why the output is inverted. That is the meaning of it. So yeah, so likewise there is one more circuit. I'll leave it to you to solve it. So the second example, I'll just change this resistor value and I will leave it to you to calculate with the different inputs. So you please work it out. So here it is given with 1 kilo ohm, this is 1 kilo ohm, and this is 1 kilo ohm. It means all these resistor values are same. Now VA, VB and VC, VA, VB and VC, and this is RF resistor. Okay, this example is slightly different here. So here we have to find the value of RF, and the inputs are not given. So here question is given that the output of the circuit must be equal to 2 times the negative sum of inputs. So let me write that here. So it is given here that the output of the circuit must be equal to 2 times the negative sum of inputs. So what does this mean? So now let us take a VA, VB and VC or our inputs. Now let me clear this section. Now the output required is that V0 is equal to, it is negative minus 2 times of this, so it is minus 2 of VB, it is minus 2 of VA plus VB plus VC. So now we know that V0 is equal to, if all these resistance values are same, so in this case all the resistance values are same, therefore this can be written as it is minus RF by R, which is equal into VA plus VB plus VC. Okay, so now if we compare this equation with this equation, then we can write this as RF by R equal to 2. Then we can find the value of RF as 2 times the value of R. So it means the value of RF should be equal to 2 kilo ohms. So this is how we can analyze this. So now, and this is a very simple example. So let us see one more example here. Design an adder circuit using an Opamp to get the output. Okay, so there is one more circuit here. Let me clear this everything. So here we have to design the circuit where we should able to get this V0 is equal to minus of 0.1 VA plus VB plus 10 into VC. Means we should able to, here the question is to find all the resistor values RA, RB and RC. So here we have to do a little assumption. We have to take any one of the resistor as some assumed value. So let us take always a feedback resistor as some assumed value. So let us take this as 10 kilo ohms. We have taken RF as 10 kilo ohms. Now we use these ratios which is given as 0.1, here it is 1 and here it is 10. Therefore we can write this as RF by RA equal to 0.1, and then RF by RB is equal to 1, then RF by RC is equal to 10. Now using these relations we can obtain the value of RA, RB and RC. So then we know that RF value is equal to 10 kilo ohms. Now this is equal to 0.1 times of 1, or we can write like this also, that is RA is equal to RF, sorry, let me write it neatly. RA is equal to RF by 0.1, and here we know that RF is equal to RB because it is 1, and here it is RF by 10 is equal to RC. So now for this case RA value we will get it as 100 kilo ohms, and this is same as 10 kilo ohms, and RC we will get this as 1 kilo ohms. This we will get it as 1 kilo ohms. So this is one kind of example which will be asked in the examination. So just we have to use a little bit of common sense and then we could able to solve this. So now let us look into one more last example for this adder circuit. So let me clear this all. So here one circuit is given, a very interesting circuit here. So there is a feedback resistor of 10 kilo ohms, and this is 5 kilo ohms, and there is one resistor here, and there is one more resistor here which is connected to one more Opamp here. So it is like a cascade example. So do not get afraid by looking at this circuit. This is very easy to analyze. Just we have to think a little bit before jumping into solving this example. So just analyze this circuit. So this is 10 kilo ohms. This is, let us rename later. So now you call this as 2 kilo ohms. This is 5 kilo ohms. And here this is given as V1 3 volts, and here it is given as 2 volts. Okay, this is minus, this is plus, and this is minus. So there is a circuit given. Okay, so let us call this a cascade section. Now if you see this part here, from here to here it is a simple inverting amplifier circuit, and from here to here it is a summer circuit with the inverting configuration. So first we will analyze this part, the first part, and then we will feed that as input to the next part, then we will analyze this. So let us call this as if we can give names here. So we know that this is V1 and V2, let us not confuse with any other terms. So let us call this as Vs, or what name is suitable here. So let me call this as V1A. Okay, so this point I will call this as V2A, and this I call this as V2B, just to avoid confusions with the same notations. So now we know that the equation for inverting amplifier, so this is given by minus RF by R into Vs. So here Vs is equal to 3 volts, and RF is nothing but 10 kilo ohms, and R here it is 5 kilo ohms. So substitute these values here, and we will get an output voltage of minus 6 volts. This is nothing but, in our case, this is V2A, because this output V0 here is also equal to V2A. So now the another input here is minus this. Now if you see this, the summer, the resistor values are not same, therefore we have to apply the first equation from our summer circuit. So this is equal to minus of, so that is Rf by, that is Ra into V2b, sorry, in this case it is Vs, this can also be written as V1a, okay, sorry for that, because we used a different notation here. So V2, sorry, let us come back to this. Yeah, so this is V1a and this is V2a plus, and this is Rf by Rb into V2b. So we know that V2a is nothing but minus 6 volts and V2b is 2 volts. So substitute these values. We know Rf in this case it is 10 kilo ohms, Ra is 5 kilo ohms, and Rb is equal to 2 kilo ohms for this second circuit. So substituting this, so just I'll write the values here to avoid the confusion for you. So it is 10 kilo ohms by Ra is 5 kilo ohms, and this is minus 6 volts, plus this is Rf is 10 kilo ohms and Rb is equal to 2 kilo ohms and V2a is equal to 2 volts. Simplify this, then we will get this final output voltage is equal to 2 volts. So this is supposed to be the answer. Okay, thank you so much for watching this session. In the next session we will talk about the summer of inverting configuration. So thank you so much.